People often say, very casually, "We're going to Mars," as if Mars were just the next city over, as if it were a slightly inconvenient vacation that requires a bigger suitcase and a longer flight. Rockets get better, computers get smaller, so naturally we just keep going. First the moon, then Mars, then the rest of the solar system. That's the story we tell ourselves. But I want to bother you right away with a question that sounds simple and turns out not to be. What do we really mean by reach Mars? Do we mean touch it like a robot does? Do we mean visit it briefly with people? Or do we mean something stronger? Go there reliably, repeatedly, safely, and come back the way we cross oceans on Earth? Because physics is very picky about definitions. It doesn't care about our optimism, our budgets, or our press releases. And when you ask the question carefully, when you follow the energy, the mass, the time, and the risk all the way down, something uncomfortable appears. Not a technological problem, not a political problem, a physical one. The kind that doesn't negotiate. And once you see it, you can't unsee it. Mars stops being the next step and starts looking like something else entirely. Let's begin with something you already understand without thinking about it. Walking. You stand up, you lean forward, you catch yourself with a foot, and you repeat. It feels effortless. But underneath that simplicity is a constant exchange of energy with the ground, friction, muscle chemistry, oxygen, heat. You can walk all day because Earth supplies you with air, pressure, gravity, and temperature that match your biology. You are exquisitely tuned to this planet. You don't notice it because it works. Now imagine walking across a frozen lake in Antarctica. Same physics of walking, but suddenly you need clothes, food, shelter, planning. Push it further. Imagine walking across the ocean. Now you need a boat. The ocean doesn't hate you, it's just indifferent. And indifference is deadly. Mars is not Antarctica. It's not an ocean. It's something far more extreme. It's an environment where every single thing that keeps you alive has to be carried, recycled, repaired, and defended against physics that never sleep. The first thing people usually bring up is distance. Mars is far away. That's true, but it's the least interesting problem. Distance only matters because of time, and time only matters because of life. A trip to Mars takes months, not because we're lazy, but because pushing mass fast costs energy, and energy has to come from fuel, which has mass, which itself must be pushed. This loop is merciless. Newton tells us that to change motion, you need force. Rocket science is just Newton being rude. Historically, we learned this lesson early. Galileo taught us that motion is not something that needs constant pushing. It needs constant stopping. Newton unified that idea and added gravity, showing us that planets fall around the sun the same way apples fall from trees. That insight lets us calculate trajectories to Mars with astonishing precision. We know exactly where Mars will be years from now. That's not the problem. The problem is that to get a human there, you don't just move a point mass. You move a fragile chemical system that panics when the pressure drops, mutates when radiation hits it, and goes insane when isolated too long. Let's talk about energy in a very down-to-earth way. Suppose you want to throw a ball. A gentle toss is easy. A harder throw takes more effort. Now imagine throwing a bowling ball the same distance. You feel the difference immediately. That's kinetic energy scaling with mass and velocity. To go to Mars, you must give enormous kinetic energy to enormous mass. Not just the people, but the air, water, food, shielding, structure, redundancy, and the fuel to slow down again when you arrive. Space is not forgiving. If you don't slow down, Mars doesn't catch you. You crash. This is where people usually say, but technology improves. And it does. But physics improvements are not like software updates. You don't get exponential gains forever. Chemical rockets are already close to the energy limit set by chemical bonds. You can't squeeze more energy out of them without changing the physics itself. Nuclear rockets help, but they don't remove the problem. They just move the decimal point a little. The fundamental issue remains. The energy cost per kilogram is enormous, and humans require a lot of kilograms. Now let's introduce a less intuitive villain, empty space. Space seems empty, calm, peaceful. It's not. It's full of radiation. High-energy particles from the sun and from deep space pass through you like bullets through fog. On Earth, we're protected by a thick atmosphere and a magnetic field. Mars has neither in sufficient quantity. During a months-long journey and then during months or years on the surface, your cells accumulate damage, not dramatic movie-style damage, subtle statistical damage. DNA breaks, cancer risk rises, nervous systems degrade. Physics doesn't kill you loudly, it kills you quietly. We know this experimentally. Astronauts on the International Space Station, still protected by Earth's magnetic field, already show measurable biological changes. Bone density decreases, muscles weaken, vision changes, fluids shift, and that's in low Earth orbit, days away from home, with resupply missions and constant communication. Mars is not low Earth orbit, it's an exile measured in light minutes. And that brings us to time again, but now in a psychological sense. Humans are not just machines that consume calories. We are social, sensory, feedback-driven systems. On Mars, there is no real-time conversation with Earth. A question takes minutes to be answered. An emergency is handled alone. Every repair, every mistake, every conflict happens in isolation. This isn't a moral problem, it's a systems problem. Complex systems fail in complex ways, and isolation amplifies failure. You might say, but we'll learn. Yes, we learn by experimenting. And experiments cost lives when the margins are thin. Historically, exploration on Earth was deadly, but Earth explorers could breathe the air, drink the water, and stop anywhere. Mars offers no such mercy. Every failure is total. Physics doesn't allow partial survival when pressure drops to near zero. Now comes the conceptual breakthrough, the idea that quietly ties all of this together. Mars is not another place. It is another regime of physics relative to human biology. We evolved in a narrow window of pressure, temperature, radiation, gravity, and chemistry. Earth is not just our home. It is part of our operating system. Remove it, and everything becomes an engineering problem with no slack. On Earth, systems fail gracefully. A power outage is inconvenient. A water shortage is solvable. On Mars, system failure is binary, working or dead. And the more systems you add to prevent failure, the more complex the whole becomes, increasing the chance that something, somewhere breaks. This is not pessimism, it's reliability theory. Engineers know it well. Redundancy helps, but redundancy has mass, and mass demands energy, and energy demands more mass. Here's a thought experiment. Imagine a perfectly sealed aquarium with fish inside. You want to take it on a long trip. You must carry not only the fish, but the water, the oxygen exchange, the waste processing, the temperature control, the food cycle. Now imagine doing that for years, with no external input, no resupply, and no natural environment to absorb mistakes. Humans are the fish. Earth is the ocean we don't notice. People often point to robotic missions as proof that Mars is accessible. And they're right, in a way that actually proves the opposite point. Robots thrive where humans struggle because robots don't need air, water, sleep, or emotional stability. They tolerate radiation, cold, and delay. The success of robots is a demonstration of how hostile Mars is to biology. Now let's reflect historically again. When we went to the moon, we didn't conquer it. We touched it briefly, at enormous cost, and retreated. The physics allowed a short visit because the moon is close, the travel time short, and the rescue window small, but non-zero. Mars is qualitatively different. It's not just farther, it's a commitment to prolonged exposure to an environment fundamentally incompatible with us. Could we reach Mars once? Probably. Could we land people there, plant a flag, take pictures, and come back if everything goes right? Maybe. Physics allows a narrow corridor of success, but that's not what people usually mean. They imagine permanence, growth, settlement, and here physics quietly shakes its head, not angrily, just firmly, because settlement means children, it means long-term health, it means accidents that don't cascade into extinction-level events, and Mars offers no stable buffer against error. Its gravity is too weak to hold a thick atmosphere. Its geology is mostly dead. Its radiation environment is relentless. Terraforming, when you run the numbers, is not a project. It's a fantasy that requires more energy than we can plausibly command. So, what does physics reveal here philosophically? It reveals that intelligence does not imply freedom from constraints. Understanding the universe doesn't mean escaping it. On the contrary, the deeper you understand nature, the more clearly you see the narrow channels in which life can exist. Earth is not just one option among many. It is a rare alignment of conditions that work together astonishingly well. And that realization is not depressing, it's clarifying. It tells us where to focus our ingenuity, not on pretending Mars is the future of humanity, but on understanding why Earth works so beautifully and how fragile that balance is. It tells us that exploration is not always about expansion. Sometimes it's about perspective. So when you hear "we will reach Mars," translate it carefully. We may send machines. We may send people briefly, heroically, at great risk. But reaching Mars in the way we reach continents on Earth misunderstands the physics of life. Mars is not waiting for us. It doesn't need us. And the universe is under no obligation to be convenient. The real lesson, the one hidden beneath the rockets and the slogans, is this: physics doesn't crush dreams. It refines them. And once you see why Mars resists us so completely, you may find yourself looking back at Earth with fresh amazement, not as a launch pad, but as the miracle it quietly is.